A lathe is a machine tool which rotates the workpiece on its axis to perform various operations such as cutting, sanding, knurling, drilling, or deformation, facing, turning, with tools that are applied to the workpiece to create an object which has symmetry about an axis of rotation. Lathes are used in wood turning, metalworking, metal spinning, thermal spraying, parts reclamation, and glass working. Lathes can be used to shape pottery, the best-known design being the potter's wheel. Most suitably equipped metalworking lathes can also be used to produce most solids of revolution, plane surfaces and screw threads or helices. Ornamental lathes can produce three-dimensional solids of incredible complexity. The workpiece is usually held in place by either one or two centers, at least one of which can typically be moved horizontally to accommodate varying workpiece lengths. Other work-holding methods include clamping the work about the axis of rotation using a chuck or collet, or to a faceplate, using clamps or dogs. Examples of objects that can be produced on a lathe include candlestick holders, gun barrels, cue sticks, table legs, bowls, baseball bats, musical instruments, crankshafts, and camshafts. History: the lathe is an ancient tool, dating at least to ancient Egypt and known to be used in Assyria and ancient Greece. The lathe was very important to the Industrial Revolution. The origin of turning dates to around 1300 BCE when the ancient Egyptians first developed a two-person lathe. One person would turn the wood workpiece with a rope while the other used a sharp tool to cut shapes in the wood. Ancient Rome improved the Egyptian design with the addition of a turning bow. In the Middle Ages a pedal replaced hand-operated turning, freeing both the craftsman's hands to hold the wood-turning tools. The pedal was usually connected to a pole, often a straight-grained sapling. The system today is called the spring-pole lathe. Spring-pole lathes were in common use into the early 20th century. One of the first lathes in the UK was the horizontal boring machine that was installed in 1772 in the Royal Arsenal in Woolwich. It was horse-powered and allowed for the production of much more accurate and stronger cannon used with success in the American Revolutionary War in the late 18th century. One of the key characteristics of this machine was that the workpiece was turning as opposed to the tool, making it technically a lathe. Henry Maudslay, who later developed many improvements to the lathe, worked at the Royal Arsenal from 1783, being exposed to this machine in the Verbruggen workshop. During the Industrial Revolution, mechanized power generated by water wheels or steam engines was transmitted to the lathe via line shafting, allowing faster and easier work. Metalworking lathes evolved into heavier machines with thicker, more rigid parts. Between the late 19th and mid-20th centuries, individual electric motors at each lathe replaced line shafting as the power source. Beginning in the 1950s, servomechanisms were applied to the control of lathes and other machine tools via numerical control, which often was coupled with computers to yield computerized numerical control. Today manually controlled and CNC lathes coexist in the manufacturing industries. Description: parts. A lathe may or may not have legs which sit on the floor and elevate the lathe bed to a working height. A lathe may be small and sit on a workbench or table, and not require a stand. Almost all lathes have a bed, which is a horizontal beam. Wood-turning lathes specialized for turning large bowls often have no bed or tailstock, merely a freestanding headstock and a cantilevered tool rest. At one end of the bed is a headstock. The headstock contains high-precision spinning bearings. Rotating within the bearings is a horizontal axle, with an axis parallel to the bed, called the spindle. Spindles are often hollow, and have exterior threads and/or an interior Morse taper on the inboard by which work-holding accessories may be mounted to the spindle. Spindles may also have exterior threads and/or an interior taper at their outboard end, and/or may have a handwheel or other accessory mechanism on their outboard end. Spindles are powered, and impart motion to the workpiece. The spindle is driven either by foot power from a treadle and flywheel or by a belt or gear drive to a power source. In most modern lathes this power source is an integral electric motor, often either in the headstock, to the left of the headstock, or beneath the headstock, concealed in the stand. In addition to the spindle and its bearings, the headstock often contains parts to convert the motor speed into various spindle speeds. Various types of speed-changing mechanism achieve this, from a cone pulley or step pulley, to a cone pulley with back gear, to an entire gear train similar to that of a manual shift auto transmission. Some motors have electronic rheostat-type speed controls, which obviates cone pulleys or gears. The counterpoint to the headstock is the tailstock, sometimes referred to as the loose head, as it can be positioned at any convenient point on the bed by undoing a locking nut, sliding it to the required area, and then relocking it. The tailstock contains a barrel which does not rotate, but can slide in and out parallel to the axis of the bed, and directly in line with the headstock spindle. The barrel is hollow, and usually contains a taper to facilitate the gripping of various type of tooling. Its most common uses are to hold a hardened steel center, which is used to support long thin shafts while turning, or to hold drill bits for drilling axial holes in the workpiece. Many other uses are possible. Metalworking lathes have a carriage topped with a cross slide, which is a flat piece that sits crosswise on the bed, and can be cranked at right angles to the bed. Sitting atop the cross slide is usually another slide called a compound rest, which provides two additional axes of motion, rotary and linear. Atop that sits a tool post, which holds a cutting tool which removes material from the workpiece. There may or may not be a lead screw, which moves the cross slide along the bed. Wood turning and metal spinning lathes do not have cross slides, but rather have banjos, which are flat pieces that sit crosswise on the bed. The position of a banjo can be adjusted by hand. No gearing is involved. Ascending vertically from the banjo is a tool post, at the top of which is a horizontal tool rest. In wood turning, hand tools are braced against the tool rest and levered into the workpiece. In metal spinning, the further pin ascends vertically from the tool rest, and serves as a fulcrum against which tools may be levered into the workpiece. Accessories. Unless a workpiece has a taper machined onto it which perfectly matches the internal taper in the spindle, or has threads which perfectly match the external threads on the spindle, an accessory must be used to mount a workpiece to the spindle. A workpiece may be bolted or screwed to a faceplate, a large, flat disc that mounts to the spindle. In the alternative, faceplate dogs may be used to secure the work to the faceplate. A workpiece may be mounted on a mandrel, or circular work clamped in a 3 or 4 jaw chuck. For irregular shaped workpieces it is usual to use a 4 jaw chuck. These holding devices mount directly to the lathe headstock spindle. In precision work, and in some classes of repetition work, cylindrical workpieces are usually held in a collet inserted into the spindle and secured either by a drawbar, or by a collet closing cap on the spindle. Suitable collets may also be used to mount square or hexagonal workpieces. In precision tool-making work such collets are usually of the draw-in variety, where, as the collet is tightened, the workpiece moves slightly back into the headstock, whereas for most repetition work the dead-length variety is preferred, as this ensures that the position of the workpiece does not move as the collet is tightened. A soft workpiece may be pinched between centers by using a spur drive at the headstock, which bites into the wood and imparts torque to it. A soft dead center is used in the headstock spindle as the work rotates with the center. Because the center is soft it can be trued in place before use. The included angle is 60 degrees. Traditionally, a hard dead center is used together with suitable lubricant in the tailstock to support the workpiece. In modern practice the dead center is frequently replaced by a live center, as it turns freely with the workpiece usually on ball bearings reducing the frictional heat, especially important at high speeds. When clear facing a long length of material it must be supported at both ends. This can be achieved by the use of a traveling or fixed steady. If a steady is not available, the end face being worked on may be supported by a dead half center. A half center has a flat surface machined across a broad section of half of its diameter at the pointed end. A small section of the tip of the dead center is retained to ensure concentricity. Lubrication must be applied at this point of contact and tailstock pressure reduced. A lathe carrier or lathe dog may also be employed when turning between two centers. In wood turning, one variation of a live center is a cup center, which is a cone of metal surrounded by an annular ring of metal that decreases the chances of the workpiece splitting. A circular metal plate with even-spaced holes around the periphery, mounted to the spindle, is called an index plate. It can be used to rotate the spindle to a precise angle, then lock it in place, facilitating repeated auxiliary operations done to the workpiece. Other accessories, including items such as taper-turning attachments, knurling tools, vertical slides, fixed and traveling steadies, etc., increase the versatility of a lathe and the range of work it may perform. Modes of use: when a workpiece is fixed between the headstock and the tailstock, it is said to be between centers. When a workpiece is supported at both ends, it is more stable, and more force may be applied to the workpiece, via tools, at a right angle to the axis of rotation, without fear that the workpiece may break loose. When a workpiece is fixed only to the spindle at the headstock end, the work is said to be face work. When a workpiece is supported in this manner, less force may be applied to the workpiece, via tools, at a right angle to the axis of rotation, lest the workpiece rip free. Thus, most work must be done axially, towards the headstock, or at right angles, but gently. When a workpiece is mounted with a certain axis of rotation, worked, then remounted with a new axis of rotation, this is referred to as eccentric turning, or multi-axis turning. The result is that various cross-sections of the workpiece are rotationally symmetric, but the workpiece as a whole is not rotationally symmetric. This technique is used for camshafts, various types of chair legs. Varieties: the smallest lathes are jeweler's lathes, or watchmaker lathes, which are small enough that they may be held in one hand. The workpiece is machined on a jeweler's lathe or metal. Jeweler's lathes can be used with handheld graver tools or with compound rests that attach to the lathe bed. Graver tools are generally supported by a T-rest, not fixed to a cross-slide or compound rest. The work is usually held in a collet. Common spindle bore sizes are 6 ohm, 8 ohm and 10 ohm. The term WW refers to the Webster Whitcomb collet and lathe, invented by the American Watch Tool Company of Waltham, Massachusetts. Most lathes commonly referred to as watchmakers' lathes are of this design. In 1909, the American Watch Tool Company introduced the Magnus-type collet using a lathe of the same basic design, the Webster Whitcomb Magnus. Two bed patterns are common, the WW bed, a truncated triangular prism, and the Continental D-style bar bed. Other bed designs have been used, such a triangular prism on some Bowley 6.5 ohm lathes, and a V-edged bed on IME's 8 ohm lathes. Smaller metalworking lathes that are larger than jeweler's lathes and can sit on a bench or table, but offer such features as tool holders and a screw-cutting gear train are called hobby lathes, and larger versions, bench lathes. Even larger lathes offering similar features for producing or modifying individual parts are called engine lathes. Lathes of these types do not have additional integral features for repetitive production, but rather are used for individual part production or modification as the primary role. Lathes of this size that are designed for mass manufacture, but not offering the versatile screw-cutting capabilities of the engine or bench lathe, are referred to as second-operation lathes. Lathes with a very large spindle bore and a chuck on both ends of the spindle are called oilfield lathes. Fully automatic mechanical lathes, employing cams and gear trains for controlled movement, are called screw machines. Lathes that are controlled by a computer are CNC lathes. Lathes with the spindle mounted in a vertical configuration, instead of horizontal configuration, are called vertical lathes or vertical boring machines. They are used where very large diameters must be turned, and the workpiece is not very long. A lathe with a cylindrical tailstock that can rotate around a vertical axis, so as to present different tools towards the headstock are turret lathes. A lathe equipped with indexing plates, profile cutters, spiral or helical guides, etc., so as to enable ornamental turning as an ornamental lathe. Various combinations are possible, for example, a vertical lathe can have CNC capabilities as well. Lathes can be combined with other machine tools, such as a drill press or vertical milling machine. These are usually referred to as combination lathes. Major categories: Woodworking lathes. Woodworking lathes are the oldest variety. All other varieties are descended from these simple lathes. An adjustable horizontal metal rail, the tool rest, between the material and the operator accommodates the positioning of shaping tools, which are usually handheld. With wood, it is common practice to press and slide sandpaper against the still spinning object after shaping to smooth the surface made with the metal shaping tools. There are also woodworking lathes for making bowls and plates, which have no horizontal metal rail, as the bowl or plate needs only to be held by one side from a metal faceplate. Without this rail, there is very little restriction to the width of the piece being turned. Further detail can be found on the woodturning page. Most woodworking lathes are designed to be operated at a rate of between 200 and 1,400 revolutions per minute, with a rate slightly over 1,000 RPMs being considered optimal for most such work, and with larger workpieces requiring slower rates. Metalworking lathes. In a metalworking lathe, metal is removed from the workpiece using a hardened cutting tool, which is usually fixed to a solid movable mounting, either a tool post or a turret, which is then moved against the workpiece using hand wheels and/or computer-controlled motors. These tools come in a wide range of sizes and shapes depending upon their application. Some common styles are diamond, round, square and triangular. The tool post is operated by lead screws that can accurately position the tool in a variety of planes. The tool post may be driven manually or automatically to produce the roughing and finishing cuts required to turn the workpiece to the desired shape and dimensions, or for cutting threads, worm gears, etc. Cutting fluid may also be pumped with a cutting sight to provide cooling, lubrication and clearing of swarf from the workpiece. Some lathes may be operated under control of a computer for mass production of parts. Manually controlled metalworking lathes are commonly provided with a variable ratio gear train to drive the main lead screw. This enables different thread pitches to be cut. On some older lathes or more affordable new lathes, the gear trains are changed by swapping gears with various numbers of teeth onto or off of the shafts, while more modern or expensive manually controlled lathes have a quick change box to provide commonly used ratios by the operation of a lever. CNC lathes use computers and servomechanisms to regulate the rates of movement. On manually controlled lathes, the thread pitches that can be cut are, in some ways, determined by the pitch of the lead screw. A lathe with a metric lead screw will readily cut metric threads, while one with an imperial lead screw will readily cut imperial unit-based threads such as BSW or UTS. This limitation is not insurmountable, because a 127-tooth gear, called a transposing gear, is used to translate between metric and inch thread pitches. However, this is optional equipment that many lathe owners do not own. It is also a larger change wheel than the others, and on some lathes may be larger than the change wheel mounting banjo is capable of mounting. The workpiece may be supported between a pair of points called centers, or it may be bolted to a faceplate or held in a chuck. A chuck has movable jaws that can grip the workpiece securely. There are some effects on material properties when using a metalworking lathe. There are few chemical or physical effects, but there are many mechanical effects, which include residual stress, micro cracks, work hardening, and tempering in hardened materials. Qed lathes. Qed lathes function similar to turning and spinning lathes, allowing for a perfectly radially symmetrical cut for billiard cues. They can also be used to refinish cues that have been worn over the years. Glassworking lathes. Glassworking lathes are similar in design to other lathes, but differ markedly in how the workpiece is modified. Glassworking lathes slowly rotate a hollow glass vessel over a fixed or variable temperature flame. The source of the flame may be either handheld, or mounted to a banjo cross slide that can be moved along the lathe bed. The flame serves to soften the glass being worked, so that the glass in a specific area of the workpiece becomes ductile, and subject to forming either by inflation, or by deformation with a heat-resistant tool. Such lathes usually have two headstocks with chucks holding the work, arranged so that they both rotate together in unison. Air can be introduced through the headstock chuck spindle for glass blowing. The tools to deform the glass and tubes to blow the glass are usually handheld. In diamond turning, a computer-controlled lathe with a diamond-tipped tool is used to make precision optical surfaces in glass or other optical materials. Unlike conventional optical grinding, complex aspheric surfaces can be machined easily. Instead of the dovetailed ways used on the tool slide of a metal turning lathe, the ways typically float on air bearings and the position of the tool is measured by optical interferometry to achieve the necessary standard of precision for optical work. The finished workpiece usually requires a small amount subsequent polishing by conventional techniques to achieve a finished surface suitably smooth for use in a lens, but the rough grinding time is significantly reduced for complex lenses. Metal spinning lathes. In metal spinning, a disc of sheet metal is held perpendicularly to the main axis of the lathe, and tools with polished tips or roller tips are hand-held, but levered by hand against fixed posts, to develop large amounts of torque pressure that deform the spinning sheet of metal. Metal spinning lathes are almost as simple as wood-turning lathes. Typically, metal spinning lathes require a user-supplied rotationally symmetric mandrel, usually made of wood, which serves as a template onto which the workpiece is molded. For example, if you want to make a sheet metal bowl, you need a solid chunk of wood in the shape of the bowl. If you want to make a vase, you need a solid template of a vase, etc. Given the advent of high-speed, high-pressure, industrial die forming, metal spinning is less common now than it once was, but still a valuable technique for producing one-off prototypes or small batches where die forming would be uneconomical. Ornamental turning lathes. The ornamental turning lathe was developed around the same time as the industrial screw-cutting lathe in the 19th century. It was used not for making practical objects, but for decorative work, ornamental turning. By using accessories such as the horizontal and vertical cutting frames, eccentric chuck and elliptical chuck, solids of extraordinary complexity may be produced by various generative procedures. A special-purpose lathe, the Rose engine lathe, is also used for ornamental turning, in particular for engine turning, typically in precious metals, for example to decorate pocket watch cases. As well as a wide range of accessories, these lathes usually have complex dividing arrangements to allow the exact rotation of the mandrel. Cutting is usually carried out by rotating cutters, rather than directly by the rotation of the work itself. Because of the difficulty of polishing such work, the materials turned, such as wood or ivory, are usually quite soft, and the cutter has to be exceptionally sharp. The finest ornamental lathes are generally considered to be those made by Holt-Zappler around the turn of the 19th century. Reducing lathe. Many types of lathes can be equipped with accessory components to allow them to reproduce an item. The original item is mounted on one spindle, the blank is mounted on another, and as both turn in synchronized manner, one end of an arm reads the original and the other end of the arm carves the duplicate. A reduction lathe is a specialized lathe that is designed with this feature, and which incorporates a mechanism similar to a pantograph, so that when the reading end of the arm reads a detail that measures 1 inch, the cutting end of the arm creates an analogous detail that is 1/4 of an inch. Reducing lathes are used in coin making, where a plaster original is duplicated and reduced on the reducing lathe, generating a master die. Rotary lathes, a lathe in which softwood, like spruce or pine, or hardwood, like birch, logs are turned against a very sharp blade and peeled off in one continuous or semi-continuous roll. Invented by Emmanuel Nobel. The first such lathes were set up in the United States in the mid-19th century. The product is called wood veneer and it is used for making plywood and as a cosmetic surface veneer on some grades of chipboard. Watchmakers' lathes. Watchmakers' lathes are delicate but precise metalworking lathes, usually without provision for screw cutting, and are still used by horologists for work such as the turning of balance shafts. A handheld tool called a graver is often used in preference to a slide-mounted tool. The original watchmaker's turns was a simple dead-center lathe with a movable rest and 2 loose headstocks. The workpiece would be rotated by a bow, typically of horsehair, wrapped around it. Transcriptional recording lathes. Transcriptional recording lathes are used to make grooves on a surface for recording sounds. These were used in creating sound grooves on wax cylinders and then on flat recording discs. Originally the cutting lathes were driven by sound vibrations through a horn and then later driven by electric current when microphones were used in recording. Many of these were professional models, but there were some used for home recording and were popular before the advent of home tape recording. Gallery, examples of lathes. Examples of work produced from a lathe. Performance evaluation. National and international standards are used to standardize the definitions, environmental requirements, and test methods used for the performance evaluation of lathes. Selection of the standard to be used is an agreement between the supplier and the user and has some significance in the design of the lathe. In the United States, ASME has developed the B5.57 standard entitled Methods for Performance Evaluation of Computer Numerically Controlled Lathes and Turning Centers, last revised in 2012, which establishes requirements and methods for specifying and testing the performance of CNC lathes and turning centers. See also, arbor support, diamond turning, segmented turning, Untitled. References. Further reading, Raffan, Richard. Turning Wood with Richard Raffan. Taunton. ISBN A1-56158-417-7 Helices, Charles. Turning and Mechanical Manipulation Volume V. Sperry, Lawrence. The Amateur's Lathe. Special Interest Model Books. ISBN A0-85242-288-1 Marlowe, Frank. Machine Shop Essentials, Q&A Metal Arts Press. ISBN A978-0-9759963-3-1 Woodbury, Robert S. History of the Lathe 1850. Cleveland, Ohio, Society for the History of Technology. ISBN A978-0-262-73004-4 Men, Women, and Recording, The History of the Office Dictation Machine by David Morton http, www.ci Rutgers EduDicta HTML. External links, Historical Lathe Archive, Medieval and Renaissance Lathes, The History of the Lathe, Early Woodworking, Spring Pole Lathe, On the Art and Mystery of Turning, Modern Machine Shop Practice. A historic Victorian text describing lathe design, construction and use in 1880s. The South Bend Lathe Library Meg Magazine, November 16, 2011. Links to How to Run a Lathe and other publications by South Bend Lathe Works. The Forgotten Power Tool. Popular Science, December 1959, ppA 149 €152. Disc Cutting and Recording Lathes. http, www.eccentric.html